I have not heard of any calculators. All right, so let's get started. So I apologize for having to cancel class on Thursday. I obviously try not to do that, but it was unavoidable. Oh, don't fail me now. And so today will just be normal lab schedule, or this week I mean. And so we'll be doing the activity series lab. And then kind of the tentative plan is, I believe on midterm week we don't have a lab scheduled. And so that can be the makeup lab for the Thursday people. And of course we could do other makeups as well. I think there's a few people who need to make up other labs. So that's kind of the plan. And then looking ahead, not that it matters too much for y'all right now. So I'm still trying to figure out the field trip. I lost my contact at the Ashland Field and Wildlife. They moved on. So I need to contact them and see if they'll let us do a field trip. That being said, so we'll move some stuff around. And so if you look at the syllabus, we have week 6 was supposed to be the field trip, but now obviously we won't be doing the caves field trip. So instead we're going to switch the labs around and do the one-pot reaction. And the only reason why I'm telling y'all is apparently they want to do a photo shoot on campus that day, and they wanted to come in and take pictures of us being all sciencey. So this is a fun lab because we're going to do a lot of things and change colors and like collect stuff. So it's a good one for them to come and photograph. So that's why we're going to skip the radioactivity, because radioactivity, it's a fun lab. You'll have fun with it, but it's not the most exciting to photograph of just like, yay, you're doing the Geiger counter. So not as exciting as like, woo, flashy reactions. So we're going to do that for the people photographing. And of course, there'll be photo releases. And if you don't want to be in pictures, right, let me know so we can obviously tell them not to capture you otherwise. No, so we're still going to do it. But like I said, right, it's just not exciting to photograph. I know you're very excited about that lab. So we're still going to be doing it. So the radioactivity lab is set for week 7, so we'll just leave it there at week 7. And then I'm hoping week 8, that's supposed to be the one-pot, maybe we could do the field trip then. Otherwise, again, we'll be kind of moving the labs around. until I figure out when we can go. All right, any other questions right now? All right, so let's finish up with 22, and I brought the demo too, like I wanted to do on Thursday. And so we left off on this problem with Tuesday. So do we get to it? Do we start it? Kind of walk me through. Now we're trying to figure out how much product is going to form. And so the first thing you wanted to do is set up your reaction just like we always do. So, right, we want to have copper 2 plus reacting with ammonia. And we might as well put in this 4 equivalents of ammonia. And so if you're unsure of the products, again, your table can kind of help you. So, okay, maybe you're not quite sure what copper and ammonia, what they're going to make. But we can look here and kind of see, well, what is on here? What are major compounds? So, right, it's pretty safe to assume we're going to be trying to form this copper ammonia complex, which is the demo we'll be doing in a little bit. So we can write our equation. So now we're here. So copper, ammonia, 4, 2 plus. And then I should have gotten my KF while I was looking at the chart. So 1.7 times 10 to the 13. And so right now, just appreciate how large that number is. That's going to come into play. All right, so where do we go from here? And I was trying to give a hint on Tuesday that we kind of have milliliter and molarity and milliliter and molarity. So what maybe do we need to do first? So let's go with what you said of let's just get the initial conditions first, right? So eventually we'll calculate how much product. But then initially I would go convert to moles, right? So we can be in the same unit and kind of do our reaction in this case. And so forgot to fire up my calculator. So let's do that first. So convert to moles. So figure out copper. And again, just kind of pay attention that we're only making one equivalent as we do these. So right, there would be 2 equivalents of nitrate, but only 1 equivalent of copper there. So converting 200 milliliters to liters, so 0.2 times 1.5 times 10 to the negative 3. And so then we get about 3 times 10 to the negative 4th moles. And then just write that you're in moles right now, so we keep it straight. And then, okay, well, we need to figure out how many moles of ammonia, right, we have left to react. Is it all going to be consumed? What's going to happen? So repeat the process. So 0.2 times, or excuse me, 0.25 times 0.2. So I get 0.05 moles of ammonia. Okay, so, right, we have, looks like more ammonia roughly than our copper. And then, of course, we have nothing initially. And then, so of course, do the reaction or our change. So then we're going to have minus x plus x. And then we can set up our equilibrium. Oh, sorry, and I made a mistake here. This should have been minus 4x, right? Because it was 4 equivalents. So that was my mistake. So minus 4x, sorry. And then x. And then, so we might as well just set up our KF formally. So our copper tetraammonia complex over our initial copper 2 plus times our ammonia concentration. Then we can, of course, substitute. So x over 3 times 10 to the negative fourth minus x times 0.05 minus 4x. All right, so what can we do with this to kind of make our math simpler? And this kind of goes back to that iron thiocyanate lab, if you kind of remember calculating that. And so not 5% in that case, because remember 5% is when it's like really tiny and not much is changing. But kind of thinking along the same lines, okay, maybe not the 5% assumption, but what is another assumption maybe we could take? And again, looking at how large this value is and kind of compare how do your moles of ammonia compare to copper, right? Which one's greater? How much will be consumed? Kind of think back to that iron thiocyanate lab. So what can we assume maybe about the copper being consumed, or how much product is being formed? Exactly. So that's the correct assumption, right? So that was the same assumption we made for that iron thiocyanate lab, right? We said, well, we had a small amount of the iron 3 plus. We overwhelmed it with a lot of potassium thiocyanate. So then we assumed, okay, well, all the iron was converted to iron thiocyanate. And so similarly, right, we're making the same assumption. So KF, oh, that was poor choice in color. So KF is large. So we're going to assume that all our copper 2 plus becomes copper tetraammonia complex. All right, so now we can basically assume, okay, our x, right? So that means if we had 3 times 10 to the negative 4 moles of copper, then of course that's going to make 3 times 10 to the negative 4 moles of copper ammonium. And so then let's go back to what it was asking for. So it asks us, what is the concentration of copper 2 plus? Well, let's finish that up here. So let's finish solving for x, right? And then we're basically going to see kind of what remains. And so now we can find our new molarity, right? So we need to find our concentration. So new molarity of copper ammonia complex. So what's our new volume? That's the tricky part. So 0.45 liters, perfect, so our total volume. All right, so now let's get our new molarity. So moles over liters. So it's 3 times 10 to the negative 4 over 0.450. Okay, looking good there. All right, so now we have our answer here. So new concentration, so molarity, 6.67 times 10 to the negative 4th there. All right, so now we can also figure out how much ammonia was consumed, right? So how can we calculate that? We can figure that out. So we have this information. Yeah, so we found X, so right, we might want to take it back to moles. That will help us, right? So if we use 3 times 10 to the negative 4th moles of copper, and then just going back to our equation, right, they're in a 1:4 ratio. So that means we use this much ammonia, correct? So then we can take our initial moles minus our final answer, right? So now we have 0.0488 moles. We can change it to molarity, right? Still the same new volume. So now this is our new molarity. Does that follow? So let me write that out. So now we want to answer, so how much ammonia left, right? Because we're still trying to answer how much copper was left. But to figure that out, we have to figure out, well, how much ammonia was left, so we can plug that in. So again, we assumed we use that much copper, 1:4 ratio gave us 0.0012 moles consumed. And then new molarity, so the 0.05 minus 0.0012 over the new volume. So that's where, again, that number came from, 0.108 molarity, again, right, of ammonia left over. And so now we can finally answer the question, or plug it in, right? So we're still trying to figure out, obviously it's going to be a pretty negligible amount of copper too, because we said we already assumed most of it is going to be consumed. But now we can finally plug it in to our KF and kind of re-verify and calculate this. So now I'm just plugging in the molarity of our copper ammonia into our expression. -4 over, so then our new molarity of ammonia times X. So now just plug and chug. So then I get a pretty small concentration, so about 3.6 times 10 to the -14 molarity, which again makes sense from what we said from our assumption and our KF formation there. Questions on that one? So let's kind of see some of this. We've been talking about it, but way better to see it. So let's go back. I'll draw it on. Yeah, I'll draw it on this page. All right, so let's look at some complexes. Well, I guess we'll look at some of these. All right, so we want to look at, again, these complex ion formations. And yes, we've been doing a lot of math, but we also just want to kind of see them in solution and see how we can demo these things. And so let's go back to copper for a second. And so let's, give me 1 second here. Oh, that's not what I wanted. Sorry, trying to do camera work here. There we go. Hopefully this doesn't freeze. Uh-oh. Come on, I didn't want all of that one. There we go. Before we do Inception style stuff. All right, that works. Sorry. Need a producer here. All right, so we want to look at the copper one. So, right, we just finished our KF formation and kind of seeing this, but let's see it in solution. And see, I didn't prepare, well, it took me a long time to get set up. So copper 2 plus in solution. Let me see if I can pull up a crystal structure really quickly. Come on. Yes, I am a human. No, I don't want to do a million captures. Oh, come on. Somebody just give me a picture. All right, totally failing to find a picture right now. So I'll try to find that later. But basically what I was trying to show y'all, or preview it to, with a crystal structure, is that, so when we have copper 2 plus in solution, and might as well let's get our copper 2 plus out. Oh, my windowed thing went away. And so it's actually complexed with some water. And hopefully I dragged enough chemicals to play with. So you all have seen copper before, this nice tealish, bluish. So just again, I'm using copper chloride as my source. 2 plus ions for copper. Just trying to make it enough. And then if y'all, you can always get closer. All right, so now it's in solution. So again, right, we're really thinking that this is some sort of aqua compound, complex, right, again, bound by the oxygen, treating it as a ligand. Again, this is donating 2 electrons to it.
Do the arrows show that it's a complex bond?
A dative bond would be the best.
A dative bond?
Yeah, so dative meaning that the oxygen is donating both electrons. So again, compared to a normal bond where they're each contributing 1 electron. All right, so let's try this. And, oh, sorry, I keep losing my window. All right, so the idea, and I'm going to try to not blow it too fast. So I'm going to add ammonium hydroxide now to this copper solution. And of course, ammonium hydroxide or ammonia, right, there's going to be hydroxide ions in there. So if I add this slowly enough, so you can kind of start to see it, there it is. And again, get closer if you can't tell. I'll shake it around. You can see it in the camera. So right, that cloudy product that's starting to form. So that's actually copper hydroxide. I don't know if y'all remember. Well, maybe we haven't gotten there. I think in the one pot reaction we'll make some copper hydroxide. Oops. And so right, it's kind of milky, but we're about to start pushing it in a second here. So I just want to draw out what's happening. So right, we had copper 2+ essentially, plus ammonia, which again, right, we're thinking is ammonium hydroxide in solution, essentially source of hydroxide. So the first thing that happens is we're making our copper hydroxide, and we can say this is solid, right? It's our precipitate. But then let's keep pushing it. So now we're going to keep pushing it until we get to the ammonia complex. It may go just a little higher in molarity. Like I said, I brought the whole chem closet practically. I'm just adding 3 molar one to get us there. It's still kind of cloudy. Pushing it. I'm getting patient. Let's try the 6 molar ammonium hydroxide now. There we go. So let me shake it. Oh. So still forming copper hydroxide. So you saw it there for a second. So we keep adding ammonia. There we go. So there's the very distinct now copper ammonia. That's okay. Make more. You just got to keep pushing right to equilibrium. Now let's see if I can turn this whole thing blue. So right, still some copper hydroxide in there. I'll add a few more, just so we can get it all nice and pretty. Just add more. Yes, that's looking good. All right, so that, once I get it all mixed. And so there might be a little bit of copper hydroxide in there. I could keep pushing it, but I'll pause there for a second. So right, nice dark blue complex. So again, let's just write what happened. So we just continue to push our copper hydroxide with our ammonia, and then it formed that tetraammonium species, just like we had predicted. And then, of course, this is also kind of pH dependent. So if we bring it back, if I add some acid to it. So add acid. And of course, right, starts to shift back to make our copper hydroxide. So of course, right, pH dependent. So let's look at another reaction there.
Are all complexes considered for stuff like this?
What do you mean?
The formation of complex, can you have complex liquid?
Well, you generally don't have liquid, but they would be like aqueous or like soluble or like what it's soluble in. And then again, in like inorganic chemistry, you generally don't use like water. So then you start shifting to organic. So like, is it soluble? THF is useful. Benzene, toluene. You don't have to go to DMSO. That's a side rant now. All right, so now let's look at what else this is talking about. And again, these are things that we can think about, but I'll want to show you. And so, right, solubility, of course, this goes back to Le Chatelier's principle. That's really what we're kind of demonstrating, right, with this back and forth. So that's always in the back of our mind. And okay, so let's start with this. And so the statement is a solubility of an ionic compound that contains a metal cation that forms a complex ion increases in the presence of aqueous ligands. That makes sense. So right, kind of getting into the series of equations. But let's look at that. And so let's just see our silver chloride. I brought, let me do the cam work again.
What is the star? Is that a plus sign?
Where?
Next to the AG, there's a plus sign.
Oh, it's just the equilibrium arrows. I think they were lost on the original one. All right, so we have silver nitrate. So remember, right, solubility rules. All nitrate salts tend to be soluble. So that's why silver nitrate, right, looks clear, aqueous solution. And now I'm just going to add sodium chloride to it. So very insoluble, which is, again, I think we all expect that. I think we've seen this. All right, so there's our silver chloride. So now I want to add to it a little bit of ammonia again. So right, that's our reaction that's shown here. So silver can make a complex with ammonia. And so let's see if we can do that, right? And we're mainly going to watch for the presence of our precipitate disappearing. And I'll start off gentle. I'll go with this 1.85 molarity. Kind of turn milky. Pushing it. Because it could have also made some silver hydroxide species. Add a little 6 molar to kick it. There it goes, starting to clear up. So we really had to push it, so it probably went through some silver hydroxide equilibrium, just like we saw before. Looks some silver chloride. So I'm going to add more ammonium hydroxide again, just trying to push it to dissolve. More of that silver chloride. A little stubborn. See if we can add more. Stir it around here. It's kind of stubborn. And then probably the silver compound, the ammonia one, is not very exciting color, which is generally expected. Silver isn't the most exciting. And so you can see if I kind of work it, there it goes, right? So now it's dissolving. So we are making our new silver ammonia complex. And again, right, we could shift the equilibrium. We could change the pH, right, add some acid, and then we probably start forming our silver chloride again. All right, so now it's got fairly clear. Check that out. And so let's try the last one that's kind of on our lecture notes. There it is. And so kind of the last scenario that it mentions here is, again, that these metal hydroxides can be amphoteric. But again, right, we want to see this. And so like you just saw with the silver, when I was trying to add the ammonia to it, right? First it went through probably a silver hydroxide complex. Again, many of these hydroxides are insoluble. But we want to look at, again, aluminum because it's a little special. And so there's kind of a lot of things that are going on with this aluminum. And so we first want to form our aluminum species, so just get it hydrated in water, and then I'll make our insoluble aluminum hydroxide, and then we'll kind of shift it both ways. So we'll start with our aluminum hydroxide compound here, and then we'll see it shift. All right, so let's do that.
Are complexes specific to metals? Are they only?
Yeah, so usually when you're talking about complexes, you're talking about metal complexes. I lost my silver. Okay, aluminum. Oh, and I forgot our other secondary cam. So I'm starting off aluminum nitrate. And I just picked nitrate because it's what we had. Prep called for chloride, but counter ion won't matter too much. All right, so there's just aluminum. But then first, we want to make, again, that aluminum hydroxide compound. And so to do so, the best way is to push it with some ammonia. Again, so our ammonium hydroxide acts as our source of hydroxide. So it should get gelatinous here. It's not being as insoluble. There we go. Sorry, I just needed stronger, more ammonium. All right, so there it is. It's coming. I'm going to shake it around. So now it's looking good. By good, I mean nice and chunky. All right, so there is our aluminum hydroxide species. So then we said, okay, it's amphoteric, so it can act as an acid or a base, and then it's going to be soluble, again, in either one of these conditions. So I'm going to just start with hydrochloric acid, see what happens. A little bit of acid-base reaction, of course, but look at how it's clearing up. So again, showing the amphoteric nature of aluminum here. So I'm just going to clear it up. Yeah. All right, so nice clear solution once more. And so that was 6 molar acid. So now let's bring it back. So we're going to bring it back, right, to the gelatinous, and then we're going to keep going. Let me get out my sodium hydroxide. Adding our base. And so okay, it's going gelatinous, which is what we expect. But then we should be able to keep pushing it. So let's keep going. Keep going. Getting nice and warm here. Neutralization. Okay, so keep going with our sodium hydroxide. Really have to push it. So I get impatient. We'll see if we have anything stronger. 6 molar. Now we're trying to push it all the way to the base. Don't know where that pH was. Let me get 12 more out, I think. Well, let me try to add a little bit more. Almost there. All right, let's drop the bottle slowly. All right, let me see if they have 12 molar. It's still pretty solid. All right, let's see if we can dissolve this. There we go. Starting to break through. All right. It's going kind of slowly. There we go. All right. Yay. Okay, 12 molar did the trick there. And so now that cleared up pretty nicely. And so again, right, obviously I blasted it with 12 molar sodium hydroxide. And then we finally went past, right, so we had to go, obviously we acidified it, and we can kind of look at what happened there. So again, we started with our aluminum hydroxide complex here, pH neutral and soluble, right? We saw that. And then we saw how we took it to the acid. And then what's kind of interesting is you have to understand at a deeper level kind of what's going on. So, right, look at how this is hydroxide, and then the ligands, right, under acidified conditions, basically our hydroxides become water, right? Well, that makes sense as we add acid. So H plus hydroxide gives us water. So then in the acidic conditions, again, we saw it cleared up. And then, of course, it took me a lot to get back. So, right, we have to push it back to pH neutral and then keep pushing it all the way to this different complex down here. And again, note that now this soluble compound is aluminum with 4 hydroxides complex on formally. So that's kind of interesting. So again, slightly different compounds, right? Just kind of appreciate what's going on. So I don't think I'm going to ask you kind of in detail, but you at least want the general overview that yes, this is amphoteric, and then kind of in the back of your mind, what you're thinking of is all these different complexes, right? That you really are looking at this aluminum hydroxide one, and then it changes to this hexa aqua one, or under basic conditions, you have this tetrahydroxide bis aqua compound. So, and then hopefully seeing that at least gives it context, so it's not just like, oh, it's amphoteric. It's like, okay, we can actually see it and make it change. And of course, if we were more bored, we could go back and forth all day with all the polarities. All right, any questions on kind of the demo or the last bit here? And then how are we feeling on the homework? Probably the only thing that I was kind of thinking of with the homework that caught my attention that maybe we didn't talk about enough was the units. For example, in class, right, we had mainly just been working with molarity, but then sometimes, or like in the textbook, it will give answers in this gram solubility. And so I just want, maybe we could go over this really quickly. Question 3, let me get a little screenshot just so you can see how to go back and forth. And again, just watch those units, especially in the textbook, whether it's giving the answer in molarity like we're used to, or, right, if it's given in grams per liter. Well, I'll just start with, right, so we usually calculate molarity, so, right, that's going to be moles per liter. So if you're given an answer in grams per liter, right, just multiply it by your molecular weight. So molecular weight, right, is grams per mole. Moles cancel. That gives you grams per liter. So then if we want to go the other way, so again, thinking about how we would normally kind of set this up or using a formula. So now we're at 1.7 times 10 to the negative 4. So it's grams per liter. But I want to get to moles, right? So we can just divide by the molecular weight, which I'm going to cheat and look it up for lead chromate. So divided by the molecular weight, which is 323, right? So 1 mole. So there we get back to moles per liter, or molarity. And so now we have 5.26 times 10 to the negative 7 molarity, or again, right, moles per liter, whatever helps you process it the best. And so then we can just continue, right, how we're used to. Just set up, again, your stoichiometry. So now I'm just kind of being formal about it. So we can see, okay, that disassociates, right, 1 to 1. So nothing tricky there. S, right, we always call our kind of molar solubility. And then S and S. So now we get to where we're probably used to of our KSP is our lead times our chromate, which is just equal to this number squared to give us our KSP value. And so then KSP should come out to about 2.77 times 10 to the negative 13. So that was just from dividing, right? So again, going from gram solubility to molarity. Yeah. Yeah, and that's it. So that's the only trick is, again, when you're calculating the KSP, you want to make sure you're in molarity. And I've noticed the textbook likes to use units of grams per liter. Again, not a big deal. Just be aware. On an exam, I won't be that picky, but again, the textbook, if you're trying to work through problems, might get confused. All right, any other questions on last week's homework? All right, I forgot to mention, Oh, if you could turn in the quizzes, if you had it, great. If not, I printed out like 7 copies. If we need more copies, I can print out more for people if it was not convenient for you to print out the quiz and do it. But yeah, otherwise, just don't forget that. All right, let's take our 10-minute break though, and then we'll shift gears and switch over to chapter 23. And I'll get, hopefully, those live notes posted. So yeah, we'll be back at noon. All right, do we all make it back? All right, so I still need to fix chapter 23. I know the reading questions aren't up yet, so I'll get those up hopefully today. And then we're kind of shifting gears now, I feel, right? We've been doing equilibrium, equilibrium, equilibrium. But now we're going to go back and finish up thermodynamics. And so let's just kind of reflect what we've learned before, right? So we did kind of exothermic and endothermic reactions, right? That was the tail end of first quarter, just kind of talking about, does a reaction need energy? Does it release energy? So just talking about energy dynamics. So we did that. And then when did we do kinetics? Yeah, we did kinetics second quarter, right? So kinetics is kind of the other half of that, of right, how fast. And so now we want to predict, will it occur? So will this reaction occur? And of course we'll be looking at some other factors, so entropy, so how entropy plays. So spontaneity, again, will it occur? So will our reaction take place? And so, right, it's a little more detailed too than just exothermic, endothermic. This is obviously a part of it, right? But even in these endothermic reactions, we're not answering, is it spontaneous, right? So that is what we're going to do today, or in this chapter. And so non-spontaneous processes will require either energy input or, and then perhaps only they go under a certain set of conditions. So again, that's kind of what we're going to be exploring in this chapter, about whether processes will occur under certain conditions. And so we'll see this, so kind of broad, but then we'll get to the quantification of this. So it's determined by comparing our chemical potential energy, which is essentially Gibbs, is where we're going, of the system before the reaction with the free energy of the system after the reaction. But again, with that, we're going to be looking at kind of heat plus S, which is going to be entropy. We're going to introduce entropy in this chapter. And so this is kind of where we're going. So the system after the reaction has less potential energy than the system before the reaction, then it is thermodynamically favorable. Again, this is where we'll be looking at both spontaneity and heat. And again, right, we're not looking at, is it going to be fast or slow, right? That's kinetics. So that's separate. Again, right, we said we have to look at kinetics data separately. So, right, we're not looking at kinetics right now. We're just saying, will it happen? So we're not saying, right, on what time scale either. And so a good example of this is diamond would convert to graphite over time. And so this is a spontaneous reaction in the sense that, yes, it will occur, but obviously this occurs at such a slow rate that I think your diamonds are pretty safe on your lifespan.
What's the slowest chemical reaction?
I mean, this is a pretty slow one. So I put this one on there. And so then we'll again look at kind of reversibility, or keep this in mind. So a spontaneous process is irreversible because there's a net release of energy when it proceeds in that direction, and it only proceeds in one direction. So thinking about our rusting of a car. And right, of course, we could do the reverse reaction of replating this, but of course that would require energy input, right? Electroplating. So it would not just occur.
When you say irreversible, you mean irreversible,
Yeah, so just like kind of what's happening normally. And then again, right, obviously we can change the set of conditions, just like I mentioned, right? You can apply electricity, then you're doing something completely different and looking at that potential. And then of course, right, we've talked a lot about these reversible processes recently. And again, we can apply this. So any reversible process is at equilibrium, and so there's no change in free energy. And so if it's spontaneous in one direction, it must be non-spontaneous in the other. So we've seen a lot of reversible processes. And so again, right, we're saying that a spontaneous process occurs since it releases energy from the system. And, right, this is kind of logical. So most spontaneous systems are exothermic. So again, right, we're just kind of thinking of that thermal energy. But this is not the complete picture. So this is, again, where we're introducing entropy. And so it mentions here, so there's some spontaneous processes that proceed from a system of lower potential energy to a system of higher potential energy. And so dissolving is a good example of that, and we'll see how it is favorable, again, once we get to it. But right, you can at least start thinking about the process of dissolving, especially like maybe those icy packs. So it's ammonium chloride, right? You break the seal, it starts dissolving, and then again it feels cold because the ammonium chloride needs that energy. But then we're still seeing, okay, well that is a process that does occur, right? It occurs very readily when you break the pack. And again, you'll kind of see where the entropy piece plays into that spontaneity, right? So that's where we're kind of going with that.
So are there any indifferent spontaneous processes?
Yeah, so right, dissolving. So we just said that that was, and so right with that, we're saying, okay, well there's two main factors that let us predict whether this reaction is spontaneous or not. And so of course it's going to be the enthalpy change, which again is our heat. Endo, exo, if you need to write that to remind yourselves, right, what we're talking about. And again, I mentioned that we're introducing entropy as our new variable here. So what's kind of entropy? Anybody, you just have like a broad definition or?
Entropy is sort of the process where if you're looking at a specific system as the escape, the irreversible escape of energy from that system.
So could we say it like more simply though?
I don't know how to say it.
Because usually I just say it's like a measure of like disorder or chaos, or like whether the system tends to go towards disorder.
Where's everything goes towards disorder?
Well, yeah, so we want to look at how that entropy changes though in the reaction. So yeah, entropy is always increasing, so then we could get into more heat death of the universe type stuff. But right, what we really want to focus on is kind of, right, this order, disorder thought. So, right, you can kind of get a taste, again, thinking of the dissolving process. Well, dissolving, right, you start ideally with a chunk of solid, and then it becomes more disordered, right, as it moves around randomly. So its entropy would increase. So kind of, that's kind of what we're going to be thinking of. And so, of course, enthalpy, we've looked at, we've defined it before, right? It's the sum of our internal energy and our PV work. Again, kind of thinking way back to first quarter, we'll review what we need to review. But right, again, that's just the definition of our energy. And then our entropy change, again, is looking at our randomness, or again, order versus disorder thoughts.
You said PV is a potable term.
Pressure volume work. All right, so then this should be a little bit of a recap, but again, right, just clearing our cobwebs out. So we said, okay, enthalpy was measured in delta H here. Typically, we saw it in the units of kilojoule per mole. And then, right, we mentioned that it's generally exothermic if the bonds in the products are stronger than the bonds in the reactants. So stronger bonds, more stable molecules. Exothermic, energy release. So again, we saw that. And then endothermic, energy absorbed. Delta H is positive. Okay, so just kind of remembering that. And so, of course, again, just spelling it out. So we're saying it's favorable then for exothermic reactions. Again, that's just thermodynamically more favorable. And then tends to be unfavorable, right, for endothermic since it needs some sort of input. All right, so now we have entropy. So again, it's a way of expressing just kind of how many different ways we can arrange the components. So technically this gets into like stat mech and probability, but we won't go quite that deep in this class. We'll save that for PChem. And so entropy, just watch the units as we do these calculations. You'll notice that they tend to be given in units of joules per mole versus kilojoules, right? So you'll just have to keep the conversion factor in mind there. And so then we have our formula here. So our entropy is formally equal to K times the natural log of W. Again, this is kind of getting into stat mech at this point. And W is just the number of energetically equivalent ways a system can exist. So again, we don't want to get too into it. But what we're trying to say is, okay, let's say we have our system here. And literally just looking at two molecules, because this is how stat mech works. And then, okay, if we open this, basically how many different ways can those molecules be arranged? And then you can start setting up, well, right, you could have 1 and 2, or, sorry, 2 could have stayed, and 1. What if both of them left? And you have 1 and 2 on that side. So right now you have, just with 2 molecules, right, all these different potential states of disorder. And so that's essentially what we're trying to quantify. But again, right, this is not too convenient for us. So just kind of appreciating this. And you can take deeper looks at this in PChem. And so for our purposes, again, we kind of want to take it more broadly. So what does lead to an increase in entropy? And so now we can think of examples. So going back to our dissolving, well, okay, right, we started with this nice pile of salt, and we could have quantified their location of all these, right? And then we can see how our entropy is going to increase, because now our one little molecule could be here, 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 right, everywhere. So now we have all these different probabilities just for one little sodium ion floating around. And so all them moving around in randomness increases the entropy. And then let's think of other things that would increase our entropy. So I wouldn't really consider it, right, because we're just thinking of just the energy. So, right, in the sense that the car hasn't changed, like state. So, right, evaporation of water is one example, again, of increasing entropy. So, of course, you had all your water just kind of in a cup in the liquid state. And then just think about the randomness, how that increases right to the gas state. Just again, more places that it can be probabilistically Just thinking of how to quantify that. And so then, kind of looking at ways that we can quantify it that work better, again, for our macroscopic purposes. So we also have that our entropy is equal to Q over T. So Q, of course, referring back to heat. And obviously, right, we can always measure our change from our final entropy minus our initial entropy.
What does T represent?
Temperature. And so then we can get this sort of formula of our heat over our temperature final minus heat over temperature initial to give this equation here. So that could be useful.
What's the difference between
So heat, it has to do with like energy that's transferred where temperature is more like absolute. All right, so now we're kind of recapping with what we need to know. All right, so then we said, first law of thermodynamics, energy cannot be created or destroyed. And again, this was first quarter stuff, but just kind of remembering. So all we were saying is our total energy of our universe is constant. So if our system gains some energy, right, then our surroundings had to lose it. So kind of remember that, right? Our energy was just transferred. And so now, let's look at our second law of thermodynamics. So the second law of thermodynamics says that our total change in entropy must be positive for a process to be spontaneous. And then, right, we're never going to have negative entropy. So entropy, right, is always increasing. So for a reversible process, then our change in entropy is just going to be 0. And then for a irreversible process, then it's going to be greater than 0. And so, right, we can have entropy of a system decrease, but then the entropy of the surroundings, right, has to counteract that and increases by a larger amount. So again, right, we're saying that our total entropy change has to be positive. So that checks out. And so again, right, if our system is becoming less disordered, so we're losing entropy, then again, the surroundings must have a large entropy. So again, we can do final minus initial. So entropy change is favorable when it's more random. And again, our entropy is positive. And so like we were seeing, right, we just want to identify scenarios where entropy is going to be increasing. So again, right, you're looking at your reaction states of your products. So a solid is more ordered than a liquid, liquid more ordered than a gas. So thinking about what's happening there. Other factors that we'll look at is how many products are we making, because again, thinking about the randomness, so if you literally have more molecules made, then you're going to have more entropy. And then increase in temperature, so of course that can always be a hint. And then again, dissolving, so that's another key there. So again, we're just thinking about our heat. So we remember that, right? Heat flow has to equal whatever is exchanged. So in this case, this is showing an insulator where no heat is being exchanged with the surroundings. but instead between the two compartments. And again, we can quantify this. So right, if we go through this, just like we mentioned before, whatever we're gaining, we have to lose by the other system. And then again, we can quantify our change in entropy by figuring out how much Q was lost, and then again, the temperature, 1 over the temperature difference between the two. And so then doing some substitution, so we have this, and again, we mentioned that our change in entropy is related to our work here. And so now we end up with this equation, so work over Q. And so basically, this is how much work then we can perform based on our temperature difference. And so this goes into things like, you know, refrigerators and how much it can cool and cooling capacity. So that is part of that. So how efficient, and how much work we can perform. All right. So now we're just kind of, again, looking at how to quantify it and predicting properties. And so again, right, we're given our Q, our heat loss has to be equal to our surroundings, so inversely proportional. And so again, right, usually when we talk about Q, we're really meaning our change in enthalpy, because we usually don't do pressure volume work. So we usually just ignore that pressure volume aspect to it. So just leaving us with our entropy of our surroundings is equal to our negative enthalpy of our system over T there. All right, so let's just try to predict our entropy. So take a minute or two to look at these. So, right, is entropy going to be increasing, decreasing? Just take some time. All right, so what are we thinking here? So we have going from a gas to a liquid. So what's our entropy doing?
It's come from a higher temperature to a lower temperature.
So then what's the sign? So negative, perfect. So right, becoming more ordered. Solid CO2 sublimes. So entropy increasing or decreasing? What do we think? So increasing, right? So it goes from a solid, and then don't forget sublimes means going to a gas. And then what about this one? What's happening here, first of all? So, right, check your states first, but then what do you notice?
You have a gas molecule splitting into two.
So gas molecule that splits, and so we look at the moles, right? We have 2 moles versus 1, 2, 3 there. So, right, we have more moles. So again, just thinking about even, our little 2-box scenario. Well, now those 3 moles of things can be in way more different, again, probabilistic potential places. So yes, is our entropy increasing or decreasing then with more moles? Increasing, perfect.
Is it fair to say that any decomposition of water molecule is a sign of increasing?
Yeah, in general. Yeah, because that's the whole definition of decomposition is one to many. So yeah, if you see that, that's a good indication. All right, so now this is just kind of defining our entropy, and this is going to be at fusion. So again, thinking of melting, freezing, back to that word. And so, geez, our change in entropy fusion would then be equal to our change in enthalpy of fusion over the temperature melting. So our melting point. And then it would also follow, so right, our change in entropy for vaporization would be equal to our change in enthalpy of vaporization for that process divided by, and so you can imagine, right, this is going to be our boiling point there. And just kind of an aside, right, if we saw the sublimation, I don't want us to forget, so right, our change in enthalpy for sublimation was just equal to, right, fusion plus our vaporization. So just keep that in mind, right, if you were ever asked for our delta entropy for sublimation. So, right, we can find that. All right, so let's keep kind of going. So now we're, again, just going to define some things now. So now we need to kind of understand where our entropy values come from. And so now, oops, we have it defined as the absolute entropy of a substance is the amount of energy it has due to dispersion of energy through its particles. Okay, so now let's define, right, what basically 0 is going to be. And so it says that if we had this theoretical, right, perfect crystal at absolute 0, so again, right, absolute 0 is the absence of molecular motion, and then, right, you would have absolute entropy would be 0. And so, right, obviously, most substances are not a perfect crystal, and obviously we're not at absolute 0, so we have some energy from entropy. And so, again, our absolute entropy of substances is positive.
Is absolute entropy always at 0?
Yeah, so this is again, right, for the perfect crystal, yeah, at absolute 0.
Not a general rule.
Well, this is a definition, right? So we have to define what 0 entropy is, right?
Yeah.
But then we're saying that, well, all our crystals are going to have some entropy.
Yeah, I understand that.
All right, so then we have to define kind of our standard conditions, right, for our entropy. And this should be, I think, familiar. So gases, remember, we're going to be at 1 atm of pressure. If we're talking about a solid or liquid, again, we'll be at 1 atm, 25 degrees Celsius. And then for solutions, be 1 molarity. again, just standard conditions, just setting up what that is. I mean, that's kind of a way to think about it, but right, it's just defining values, right? So eventually we're trying to get to entropic values that are in the book, but right, we have to kind of define, well, how do they even come up with any standard definition? All right, so then, again, we've kind of been looking at this, so we're just kind of building up to the math still. So we set a process in which the final condition is more random than the initial. So of course, our change in entropy is positive. And so it's favorable for the process to be spontaneous. Again, right, we haven't really said whether it's spontaneous. It's just, that's a good indication. So we're still kind of building. And then if the final condition is more orderly, then of course, the change in entropy of our system is negative. Like we mentioned, again, entropy is always changing. And so this is just another formula, and hopefully this form kind of reminds you of something. So what does this kind of look like? Do we see something maybe first quarter that look kind of like this? Where else do we take the sum of the products minus the sum of all the reactants? It's something we were talking about too, whatever variable we're talking about. Yeah, so it's very similar to the enthalpy calculations. So, right, I'll just say, kind of recall, we had the same formula for our delta H of our reaction, right? Remember, it was the sum of the delta H of the products minus the sum of the reactants, right? All multiplied by the molar amounts. Does that kind of ring a bell to people? I remember that. And so again, this is kind of where we're building to with that set. And so again, now we're looking at our entropy, so just defining when to use a chart essentially. So entropy is an extensive physical property, so it doesn't matter on the substance. So entropies are for 1 mole of substance at 298 Kelvin at a particular state for a particular allotrope, which we'll see what I mean in a second. And again, right, for a particular degree of dissolving, so going back to 1 molarity of solution. Oh, where's my table? Okay. Apparently my table disappeared. Oh, here it is. It's on this page. There's my table. So this is, again, just an example. And so this would be right from the back of your textbook or something. So right, just our standard entropies. So just like, right, we have standard enthalpies of formation, we have standard entropy. And so again, now we're just kind of appreciating the numbers. And right, we expect them all to be greater than 0. So we said that, right? We're not at absolute 0. We can appreciate, right, we got carbon here as a solid, and then it has a note on it. So let's look at that note. And so this is what they're implying by the either allotrope or geometrical structure, right? So this is going to be for carbon, but in the graphite form. So if we wanted the diamond form, for example, right, we'd have to look up another table or another reference sheet.
Is graphite like the most entropically favorable crystal structure of carbon?
I would assume so, since it's the most thermodynamically favorable. Unfortunately, they didn't have other. I was really hoping that they would put the other allotropes on there, but we could try to see what's in here. So again, right, this is just a more detailed book. So your book obviously has a table with a bunch of stuff. If you get really bored, right, we have those reference books in lab with, I'm sure, a ton of thermodynamic data. And so this is, again, a standard table that you might see with some of our familiar values. So, right, again, there's good old enthalpy, just like we did before. And now we have the addition of entropy. Again, just kind of taking it in right now that there's obviously a bunch of different forms. See if we can find carbon. So look at carbon. So, right, carbon in the graphite form. Actually, the diamond has a lower entropy. So I guess there's more to that than we expect. So diamond has a higher enthalpy though, so that's probably something to do with the stability. And then is that carbon gas? That's kind of odd, but that's there. So again, write all your substances, blah, 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 so you can knock yourself out. Just trying to see. Here's another example of, again, some different allotropes. So white phosphorus, solid versus P4. So different forms. Okay, so that's just, again, telling us, right, that there's a bunch of reference tables. Oh, I lost my pen. Oh, what did I do with my pen? I dropped it somewhere. Oh, I need my Wacom pen. So I need the pen. That's annoying. No idea where it went. Oh, there it is. Okay. All right, so now, again, we're just appreciating the values, right? So we're just kind of saying some obvious things. So if it's a gas, it's going to have a larger entropy. Okay, that makes sense. Let's look at other trends. So we see the larger the molar mass, the larger the entropy. So again, just appreciating that. So it might help us.
Would the plasma have a larger entropy than gas because of the diluted form of the atoms?
Yeah, I mean, it'd probably have a high entropy, but yeah. Plasma is just not like, it's just a fleeting state, you know, so we're not going to like be studying it normally. And then, so again, how constrained it is. So diamond having the tetrahedral structure gives it a slightly lower entropy than graphite. But again, right, like we mentioned, not the complete picture because we said this was spontaneous, right, going from diamond to graphite, which is where we're getting at, is when we need the complete picture of our enthalpy and entropy. All right, so now we've landed at kind of the sum of in our math here, so where we've been trying to get to this whole time. And so now, right, to actually quantify it, we need to look at this new variable called Gibbs free energy. And so a process will be spontaneous, and make sure you highlight this when our change in Gibbs free energy is negative. And so then we'll have a various set of conditions. And so again, we'll look at this kind of broadly and then get into the details of quantifying it. But just overall, so our delta G will be negative if we have, of course, an exothermic process, right? So our change in enthalpy is negative or exothermic, and our change in entropy is random. And again, right, just kind of think about it. That makes sense, right? If something is exothermic, it's releasing energy, and then it's also going to more randomness. So that is a spontaneous process. And then you could also have certain conditions, and again, right, we'll quantify it. But, so our change in enthalpy could be negative and large, but then, right, maybe our entropy is negative and small, but as long as, right, our change in enthalpy is large enough, it can overcome this, right? Or perhaps, right, we do have an endothermic process like we'd mentioned, but again, maybe that is small enough such that the change in entropy, the increasing entropy, again, right, going back to dissolving something, maybe that will be enough to keep it going, is what we're saying there. And then, of course, these are conditions where it will likely not be spontaneous. So again, a positive delta G. So of course we could still have an exothermic process, but then if we have a small change in entropy that is negative and large, right, it may not be enough to overcome that. So if it's becoming too disordered, or perhaps at high temperatures, so again, we will quantify this. We could also have a scenario where we have an endothermic process, and again, our change in entropy is maybe just small, or it's at a low temperature, or we're not getting enough energy, right, so it doesn't happen. Or we could have this scenario where it's an endothermic process, and then our entropy is decreasing, and then we will never have this reaction occur. And then if our delta G is at 0, then we're at an equilibrium scenario. So kind of, I just want to pause there for a second. Questions on that? Because that's a good, like, thought overview, right, of where we're going. So we want to make sure we at least understand this with the words before we start putting, right, all the math to it. Does that kind of make sense in what it's saying?
I guess that question about the second bullet point there, the change G was it says that the change in P is negative, the smaller the change of entropy is negative and large. Can that be condensed down so the change of H is greater than change of S with both negative?
Essentially. So we'll see that with the formula. So that's, yeah, that's basically where we're going.
These notes are all going to be online.
Yeah, so they should already be hopefully posting. They should be updating. All right, so now let's keep, so now we're getting to quantify it. And so again, we can kind of relate this to maybe our equilibrium a little. So our Gibbs free energy, again, just tells us what direction it's going to be going. And just looking at our Haber-Bosch process, again, all we're saying, if we're moving in this direction right now under these certain conditions, it doesn't really tell us, I'm not sure what this axis is, just the quantity maybe, or our yeah, this is the Haber-Bosch process. Hmm? I mean, it's just how you make ammonia. Yeah, that Haber-Bosch, I think. Yeah, I think it's the Haber-Bosch process. At least that's how I've heard it pronounced. But again, all we're saying, so the Haber-Bosch process, it's just a fancy word for the ammonia reaction. And obviously it's really important because we need fertilizer, but it also occurs under pretty forcing conditions, which is why it comes up in this sort of discussion, because it occurs at extremely high temperatures and pressure, also very energy intensive, so not the most, what do you call it, nature-friendly process in that sense. But again, right, we're just saying, okay, we can kind of use our Gibbs to tell us which direction it's going. And again, right, equilibrium. If our G is 0, then we know we're at equilibrium there. All right, so now let's get into our quantification. And so blah, blah, blah. So let's kind of skip. So we have our Gibbs free energy is, again, the maximum amount of work that can be released to our surroundings, and sometimes referred to as chemical potential. And so this is our important equation, right? So now we can say that our change in Gibbs free energy is equal to our change in enthalpy minus our temperature times our change in enthalpy, or entropy, sorry, entropy. And so again, right, you can kind of stare at this formula and go back to the words, or this chart is also kind of a good, again, summary of all those words that we just said. And then again, our change in entropy of our universe determines whether our process is spontaneous. And again, delta G is really what we're looking at. And so this is just a summary of kind of, again, those words, right? So again, we have an exothermic process. Our entropy is increasing. And so then it's telling us when it's going to be spontaneous. So again, delta G has to be less than 0 by definition. So it's going to be spontaneous at probably low temperatures, high temperatures. So I would expect this to be, right, spontaneous probably at all temperatures, since again, that's favorable, right? Exothermic, increasing entropy. And so this is just one example. Again, we're seeing how our entropy increased with our number of moles. And then not clear that this is an exothermic process, right? But we could figure that out, right? So we can go back to our enthalpy values, just like we did first quarter, and calculate that.
Are there any other conservation laws when it comes to this, or is it all just based on conservation?
Yeah, because this is our laws of thermodynamics. So this is basically summing it all up now, right? So before we had a very incomplete picture because we only looked at enthalpy and exo-endothermic reactions, but the Gibbs gives us, right, the true picture. So that it gives us the enthalpy and the entropy combined, and will there be energy for it to occur? And again, right, just this follows with the chart. Oh, I guess we're running out of time here. So right, follows with the chart. Again, endothermic process, decreasing entropy, so not going to be favorable. And so this is probably going to be non-spontaneous at most conditions. And again, right, we could try to quantify that. If we have an exothermic process with, again, decreasing entropy, so it, again, will be spontaneous probably at a low temperature, as long as our delta G is, of course, less than 0, and then probably become non-spontaneous at a high temperature. So thinking about ice going from a liquid to a solid. So again, right, that makes sense. So that would occur at a low temperature to get freezing. And then again, our last scenario, endothermic, increasing entropy. So then we'll find, right, it's probably not spontaneous at low temperatures, but then give it enough energy and it will be. All right, so we'll probably stop there since we're out of time. But you can see, right, what the last little bit is going to be. And so now we'll be kind of putting the math together. So we'll be going through that. And then again, just kind of calculating and relating it to good old K here. So we will do G and K as well. So just be prepared on Thursday for some math. And otherwise, I will see y'all in lab. If I need more quizzes printed, let me know. It looked like they kind of all got eaten up. So if you didn't get a quiz copy, I'll just go make some more.
I won't be here Thursday. Is it okay if I make it to the quiz later?
Oh, like the quiz, the future quiz later, you mean?
Yeah.
Yeah, that's fine.
On Thursday, yeah.
Yeah, did you want to do lab today or just?
Yeah, I'm going to do a lab today.
Okay, sweet.
Thank you.
See ya.